So good morning. I really appreciate that you showing up, on time. I didn't expect that the day 3 in the morning is the hardest thing to motivate yourself. But I'm here, Asada from MIT, and then I'm going to talk about the control coherent Koopman modeling and its application to some of the hard problems in robotics. Let me start with a very negative slide. We hear criticisms of Koopman things by controls and the robotics community. They say that traditional methods outperform the Koopman operator method. Why should we bother with the Koopman, right? And some said the sort of robotics controlled with the Koopman makes sense, but not much, other than that and controlled robotics. And so I know within this nice community of Koopman, we praise each other, but we really have to thank the people outside of this. And to me, there's not so much actually, really we have convinced those people. And I think that's one of the very serious issues, and we have to think, what's wrong with us and how we can really convince them. And I raised two issues today. One is that, and as far as we apply this to robotics and controls, we haven't solved the fundamental limitations that are actually not applicable to non-autonomous systems, right? And we have actually, nice, controls, B times UT, but B is in fact in the state dependent, and we just, yank, and then that's, approximated to a constant B, which doesn't work, when B changes broadly. So people just look at the some, more, benign nonlinearity where B X doesn't change very much, but it's not so much actually impressive in applications. So we've been doing somewhat of hand-waving things in the B matrix, but I know in control, theory viewpoint, the B matrix is so important. If you just make a bad B, it's a misinformed controller. So it's more serious than the error in A. Next one, we really have to think about some killer app, something that actually clearly moving the yardstick to next level. And then I'll pick some of the switched systems or hybrid systems. So today, first part, control coherent Koopman is kind of emergent techniques that doesn't require any approximation to B matrix. B is exact and constant. And then I've already presented the actuator dynamics approach. If time permits, there's some important extension to actuator pre-filtering approach, which significantly reduce the constraints on it and brought on the applicability. And the second part, I look at the switch dynamic system that we see often in robotics and locomotions and contact-rich manipulations. And that seems to me the killer app of Koopman. So starting with the first one, control coherent Koopman modeling, we start with the there's a standard discrete time nonlinear set equations with the control UT. And the key concept involved is that we split the state variables xt between the state variables related to the actuator side and the plant side. And the actuator side, we assume that the control input, the BT UT comes in, appears linearly into the systems. And then actually the actuator dynamics itself is very highly nonlinear, but a key point is that this one is to show up to the linear contents. And I can show you that this particular form can be seen in conditions of satisfied by the broad range of systems of practical interest. So we start with the forming the forming the autonomous systems associated with the original non-autonomous systems, eliminating the control term BUT, and then this turns out to be just a standard Koopman program. The resultant matrix A, however, must be valid in the original systems, and all the dynamic range on actuator dynamics is to be driven by UT, and then that this guy must be bodied in that range. Now with that, yeah, we can under some mild assumptions, we can reduce that original form into this nice the Koopman operator form with the constant B matrix of B times the UT. And then I divide the lifted state variables into two parts. The first part is basically actuator state variables PT, and the rest of the part is basically other observables and put into YT. With this, actually, the divisions matrix A can be broken down to 4 blocks, and the upper part is related to the actuator state transition PT. And then that one, first line, we can get the first rows, FP bar equal APP PT plus AY, APYYT. And by simply adding control term BP UT to both sides, we get to this equations due to superpositions. And then this one is to give the original state equations, and combined with the reformulating this, and we can put into this combined with the front side of dynamics, which is also represented with this linear things. And so B matrix consists of original BP and 0. Now, as I said, this can be found reasonable, formulations in many systems, starting with the just a canonical program, standard robotic systems, having some harmonic drives and gear trains, which is quite compliant. So if that's the case, joint angles and then actuator displacement are independent state variables coupled with some compliance here, and then that satisfy. And then the here actuator dynamics with the actuator torque applying here, that's shown up linearly because the actuator rotor inertia is constant, satisfying all the control coherence Koopman assumptions. Same thing applies to hydraulic and pneumatic systems. Due to the compressibility of the fluid, it has some compliance here. And then actuator side of the dynamics, in terms of the spool dynamics and having a constant, mass ms, and then actually, some magnetic force applied to it, and basically forming the linear equation where controls, appears linearly. Also interesting is that we also apply this to a biomechanical system. Muscles have both parallel and serial compliance, and they satisfy these conditions. It was a very big surprise. So all these actually, we can formulate it, CCK. So with this actually control coherent Koopman, how we can actually apply this to something important and hard problem. In the robotics, I see that the hard problem comes from somewhat and actually, switching hybrid nature of the dynamics, and then gate dynamics in particular. You have at least 2 dynamic equations switched back and forth. Both legs are in contact with the floor, or one leg and only contacting the floor. You have to switch to 2 dynamics and back and forth, back and forth. Manipulation too, as things in contact with this, it is impacting the dynamic equations. So it's hard to see the global picture, global behavior, if the system is basically segmented into many sections. And if you just apply the model predictive control, it turns out that just a mixed integer nonlinear program. This is hard. The state space is divided into many segments, and each having specific dynamic equations. And then in this formulation, an integer variable s is actually take 0 or 1, and only one is selected, picking up a particular regions to apply to this dynamic equations. Looks like a unified representation given there, but S times F, FD is basically domain dynamic equations must be switched. So having the integer S and continuous variable state X, both are involved. This is the mixed integer problem, hard to solve. So I propose to use the Koopman operators as a mechanisms for unifying the otherwise segmented switch dynamics and subsume each switch to each segmented dynamics within a global linear model, which is very much amenable for control. So start with the switch dynamics, and then we convert this to a Koopman compatible physical model. In doing so, we take care of we address the discontinuity and causality, and then whether the system satisfy the control coherent conditions. We got the some Koopman compatible physical model ready for lifting and linearizations. The resultant model is linear time invariant systems. MPC can be applied in a very straightforward way. It is a convex optimization, very quick to compute. And I demonstrate this with the two major fields of robotics. One is locomotion, the other is manipulation. So rimless wheel is the simplest model of explaining a human gait. And just rip off the rims of the wheel and then on the spokes that represent the human legs, and then one point of contact and a 2-point of contact, and then immediately after that, next legs comes in, which is actually the next spoke comes in. So this is a very simple model. Now we make it actually active. So spoke is driven with some actuators, and that's actually possess the state variable to phi I. And so, generally the coordinates of the systems are x, y, theta of the hub, and then an actuator spoke of phi I. These two sets are independent general coordinates when the system is not in contact with the floor, but once it's in contact with the floor, the conflict occurs because x, y, theta positions and the phi I cannot be determined, cannot be specified independently. To resolve this conflict, causal conflict, we use elastic floor. But this has been actually used in the leg locomotion community quite extensively, having some appropriate compliance here and solve the discontinuity of a problem, at the same time even improve the performance. So we consider this, and for the contact model, we can apply any sophisticated one, such as this nonlinear models, no problem. About the actuator dynamics, we look at the equation of motion of the actuator and stuff. And IM is actuator-related inertia, which is constant, and then it's subjected to ground reaction force, which is highly nonlinear. And UI is the actuator magnetic force or torque, which appears linearly because IM is constant. So that actually conditions are met. So CCK, control coherent conditions are satisfied. Okay, so just to summarize this, the actuator dynamics side, it is in the form of some nonlinear term, FP, PT, QT, plus control terms shows up and linearly BP, UT. And then, the plant side of dynamics, very complicated, but doesn't matter. We can put it into that, control coherent Koopman model, as shown there, where the ZT is basically consisting of actuator state and then rest of the part. And the B matrix, basically consists of constant parameters. So here, IM is inertia parameter. This could be, obtained through, the data-driven method too. Now, after determining B, we can determine the matrix A, and then you can run the, all kind of, simulations and tests. And it must be, persistently exciting in the data set. And now, in determining A, because we know the B, and then we measure the UT, so we subtract the effect of the actuator. So from here, because of the linearity, we can determine the A matrix in a very straightforward manner. So applying this to MPC, we got the kind of nice from along the time horizon. It may actually include no contact case or 1-point contact, 2-point contacts. In fact, the switching occurs in the original state space, but actually lifted the space. It is just the linear systems. Now, this shows some quick animations, simulation and results. It finds some way of coordinating multiple actuators to move forward. In fact, this is not so much a simple job. The system has to discover how we can actually coordinate that moving forward. Yeah. Now, and then this guy is the, just a printout of the whole, events happening here. It includes many different stuff. And one tricky thing, and an interesting point is that we must have certain, time horizon. If time horizon is actually significantly, long, it can predict what's going to happen after switching, after beyond the border of switching, what's going to happen. But if it's too short, it doesn't see whether this one switching is, is useful or not. So that's all about the leg robotics. Now this applies to non-prehensile manipulation, pushing the shoving. This is the state of the art. About 5 years ago, my colleague Alberto Rodriguez group did it, and it's a very high impact work at that time. And the robot actually tracked this guy using MPC, and it's contacting here. But a big assumption is that the process must be quasi-static, and the contact must be maintained. Once it is actually departed, they can't actually deal with the situation. Some similar works, they assume some sequence of contact and non-contact stuff is given, or the reference trajectory is given along which linearization is made, and some offline computations. But what I like to do is something like this. The real system is much more dynamic, right? That's not the within the scope. So no dynamic process, no sequence of contact is assumed, no reference trajectory is given. Everything must be done in real time in a computation. So this is the systems where we implemented and demonstrated the CCK and PC. We assume that the high fidelity velocity control of the robot side, which means that you command the desired velocity UX UI, and then that will result in the particular position XP YP, just a simple integrators. Well, this is the linear, and then input the UX UI shown up linearly. Now, yeah, so XP YP the actuator side of state variables, and actually plant side. This slider consists of 6 state variables. When actually pusher is not in contact with this, these two independent, but they are contact, they are dependent. But we assume that the pusher is somewhat compliant, and then we can solve this conflict of problem. And then the rest of the part is slider the dynamics as opposed the dynamic equations. Now, so we first actually started with the compliance and actually eliminate the discontinuity and applying the CCK. And then next we use the deep neural nets and then going through this CCK formulation, end up with the MPC. So this is the one result. Initially, the top right figured, initial pusher position is actually that side, star side, and then we want to push the blue plates to right-hand side. Now that actually initial position is not the right position, and actually MPC discovered that it's a wrong position, have to go around, detached from the object, and move to a next point, and then go around this. If the friction is a little too small, it's more erratic, but going this and still manage the manipulations. So this one is kind of dribbling mode and very reactive, and then it can actually find the right sequence where to contact and actually contact, it's basically controlled by the MPC controller by itself. No predefined contact sequence, no quasi-static assumptions needed, and all running at the real time. Now, real timeness is so important. And then let me actually show you this. This is really the most convincing part. We measure the runtime. Only 5 milliseconds is actually sampling intervals needed. This is almost 100 times faster than the conventional counterpart. We even actually compare this one against the bilinear Koopman, which is not actually convex optimization. It takes actually 50 times more time. Now, yeah, so it is like a quick stuff so we can react to that any kind of disturbance and very effectively. Now, but I know, as I said, the real players here is the kick or the shoot, not just a dribbling, right? How can we actually, this robot can find a way, how to switch and then, combine these two different modes. One is actually this kind of shoving, the other is actually, dribbling. Now, interestingly, using the same control framework, MPC, but if you just change the weight matrices, Q penalizing the tracking error, we penalize more, and then control side penalty is smaller, and you abruptly change the goal, the far point. It turns out the MPC controller, determines the shoveling as opposed to the dribbling. And then that kind of a switching is to occur automatically. Now, parameter studies are very important in this case. So we really hinged on a couple of parameters. One is flow of friction. This shows that what happens if the systems overestimated the friction. In fact, the friction is much, much smaller, more slippery. This is the case, a correct one. It's nice actually, find the dribbling, but it's more slippery. It's overshoot, and then catch up with it, and actually a little bit of, performance is deteriorated. To cope with this, we applied the friction-aware deep Koopman network, where friction parameter mu is treated as additional state variables, putting into this, and we train the system for different values of friction. And then actually, friction can be estimated from the performance in real time, and then evoking the right, A matrix and use that. That sort of, adaptation can be done. And with that actual use of that adaptation, control performance against the friction and the discrepancy, the larger here, the performance gets worse. But with the adaptation, this blue lines, it's basically very uniform performance has been obtained. You are still somewhat speculative and then maybe doubtful about the compliance in there, right? You may say, what if the pusher is much, much stiffer? Does it impact the Koopman prediction accuracy? Is there any fundamental limitation to this method? So we look at the effect of the stiffness against the prediction accuracy, first prediction accuracy against the stiffness in a logarithmic scale. And if it's extremely stiff, the prediction accuracy goes bad, really bad. If that's a compliant here, down here, it's better. But other things, it's too compliant, then sort of control authority goes down because actually, you push this guy by moving here. If the cage is too small, some bandwidth issues comes in. We characterize this as the inverse response resonant frequency, which goes down as the orange line going this. So somewhere in the middle, we have some sweet spot. that actually makes things very good, working well. And then we plot the MPC cost functionals values against the stiffness, and somewhere in here it is very much acceptable performance. So we learned two things. Yes, if stiffness is too high, this method does not apply. But at the same time, I have to say that in a sense, in the context of robotics, compliance at the tip may be a design parameters. You can pick the right one, to guarantee the good performance. So just to summarize what I talk about today, we started with the switch dynamic systems and then converted to Koopman compatible physical modeling by checking the discontinuity and then control coherent, Koopman requirements, and then apply the MPC, which is actually convex optimization very fast, and demonstrated with the two representative examples. So this is summary. I think I have just one more minute, okay? This is my recent journal paper, and we extended the CCK conditions, not relying on the physical properties. We assumed some compliance between the actuators and the load here, right? But what if direct drive, there's no gearing, all solid? Well, we can actually take the following techniques. Instead of relying on the physical compliance, we can make the this process to be through some dynamic filter. So don't put the control input directly to this, but through some dynamic filter, which possesses the independent state variables. So this part is the same story. And then here the linear filter, so control input appears linearly in the system. There's some interesting, so this is more generalized the linear filter case, and we assume we can prove that as a case. So that's some interesting control performance, system tuning with respect to that dynamic filter. So just to conclude this, I want to just make one important, my view. I see Koopman operators are catalytic operators to convert a dynamic system to causal, actionable embodiment. Some in robotics, in the system in particular, kind of hybrid systems, switch systems are harder to characterize. But we bring in a catalyst and a Koopman operator together with the machine learning, convert it to globally linear unified model. This is really big chemical reactions to get a very amenable form of dynamics. And so this form, this actually structure is applicable not only robotics but in many other areas. So I see this one as kind of more generic modeling approach that can be applied to broader systems. So that's what I say. Thank you.